Good day, I am Mikhail Goldonis, and for my course project in Data Communications and Network Theory, I was tasked to create a presentation regarding the pool of topics of my choice. And at the end of the presentation, I am to show a demonstration of a network topology and the corresponding routing procedure in Cisco Packet Tracer, and the pool of topics that I chose were dynamic routing, EIGRP, and EIGRP tuning and troubleshooting. So let's get right into it. First of all, let us go with dynamic routing, which is one of the core topics of this course. So dynamic routing is a method where routers automatically share and update routing information as opposed to static routing, which is static. It doesn't move, and whatever IP addressing is or assigned to the various end devices in the end devices and the routers and such in the network topology. That's it. For dynamic routing, um, the routing procedure adjusts to network topology changes without administrator intervention, which is hence why it is called dynamic. And through this, it helps support load balancing and route summarization, which we will go into a little further down the line. So first, dynamic routing may fall under two categories. The first is the IGP, or Interior Gateway Protocols, which means that dynamic routing happens within one organization, and that means that it only the dynamic routing is followed within the certain network topology that it is implemented inside. And such examples of dynamic routing that fall under interior gateway protocols include routing information protocol, open shortest path first protocol, and EIGRP, or what we are going to discuss later, enhanced interior gateway routing protocol. And the next one, or the other category that dynamic routing is under, is exterior gateway protocols, where dynamic routing occurs between organizations, meaning there are no boundaries. So, an example of that is BGP, which is the Border Gateway Protocol, which is basically how our internet works. Yes, the internet that we use in our daily life. That is basically an example of BGP, or BGP, or a routing protocol that falls under the exterior gateway category. So yes, we can move on to further examples of dynamic routing, or let's say subtypes of dynamic routing. The first one being distance vector protocols, or hop or dynamic routing protocols that use hop count to determine that use hop count in order to connect devices together. Hop count being the number of intermediate devices that a packet or packets have to pass through in order to reach their end device. We will know what packets are later. And an example of this is the routing information protocol, or RIP, one of the very first protocols implemented in networking. And then next we have link state protocols, which use the full network topology, find cumulative bandwidth, and calculate costs. Unlike distance vector protocols, link state protocols analyze all the connections that are present within the topology instead of only the intermediate devices or routers. Yes, instead of the intermediate devices or routers that are located in the topology. So the end devices are also scrutinized in a link state protocol in order for routing the dynamic routing procedure to be implemented. And an example of that is the open shortest path first protocol. And we also have over here classful protocols, which do not need some masks, such as our original routing information protocol, or RIP v1. So this very first routing protocol, the first ever routing protocol, which is a distance vector, is also an example of a classful protocol. And as a result of having no subnet mask, it doesn't need VLSM, or variable length subnet mask, and CID, or classless interdomain routing, since obviously it's classful. And CIDR obviously falls under classless protocols, which send subnet mask info and support DLSM and CIDR. And the examples of these are more complex and definitely more advanced and more effective routing protocols such as EIGRP and OSPF. So EIGRP, we are going to discuss that later. In dynamic routing, the shortest path is constantly pursued. So yes, I keep mentioning OSPF, open shortest path first, and it is based of course on first the shortest path first fundamental theory, which is in a method of advanced path selection. And this method of advanced path selection is based on Dijkstra, I'm sorry if I'm butchering his name, Dijkstra's algorithm, which builds the shortest path tree using cost. And if you do not know who Dijkstra is, he is a Dutch computer scientist who happens to be the very first person to solve the shortest path problem. So if you remember in subjects like discrete math and such, you took them earlier in your college studies, wherein there are polygons drawn or whatever shapes. There are multiple lines drawn on inside these polygons with multiple points, and you have to see which for example, the teacher gave you a problem to find the shortest distance from point A to point E. That is basically a shortest path problem. And Edgar Dijkstra, I'm sorry if I'm butchering his name, he was the very first person to solve that problem. And that problem, which the solution, which became Dijkstra's algorithm, was implemented in the foundation, or was a core foundation in the implementation of routing protocols. And most routing protocols fall under or base their operation on the stress algorithm, except for EIGRP, which uses a different method, which is dual or diffusing update algorithm. And we will get into this certain type of algorithm later. Well, actually, not that much later. We're gonna get into it right now, since we are going to move on to another main topic, the very main topic of our presentation, which is EIGRP, IGRP, or Enhanced Interior Gateway Routing Protocol. It is the successor to IGRP, or Interior Gateway Routing Protocol, which I did not include in this presentation, but it falls under a distance vector protocol, I believe, and that means it is a very efficient and very ancient routing protocol. But EIGRP replaced it around 1992. The reason for its replacing of the IGRP includes fast convergence and low bandwidth use, and it also sends hello packets very often in order to maintain connections, while also using the dual algorithm, which I mentioned a while ago, which is basically implements route advertisement and neighbor info in order to attract or to create connections between different routers in a network topology. And route advertisement is a key feature of distance vector, while link state protocol the distance vector protocol, while the link state protocol uses neighbor info. And since IGRP uses two of two very core features of previous routing protocols, or subcategories of different routing protocols, IGRP is considered a hybrid routing protocol. Therefore, it is very, very advanced. And of course, it is expected for an advanced routing protocol that it will support BLSM, CIDR, and therefore route summarization. And this route summarization also helps load balances across equal and unequal cost paths, and making it basically loop free. So there we go. More on EIGRP. These are the packets that I was mentioning a while ago. So EIGRP uses different packet types and messages to help facilitate establishment. The very core of EIGRP is the hello packet, which aids in neighbor discovery, and it is used to form adjacencies between different routers. And after the hello packets are sent out, we also have update packets, which advertise routes, that existing routes to other routers within the topology or within the network. And there are also queries or requests for routes, or basically requests for the foundation of routes between two routers in a network topology, and then a reply from the other router, the router that is receiving the request or the query, and then also the acknowledgement, which acknowledges that the route has been secured, that um the two routers have agreed to meet halfway. So basically, EIGRP also relies on route reliable transport protocol, or RTP packets, for delivery. And over here we have a few images that are used, that basically show the mathematical equations, or the mathematical equation and the constants needed to consider the calculation of EIGRP. So this is basically a metric to determine the EIGRP of a certain network over here. So we have bandwidth, load, delay, and reliability. K1 is bandwidth, it must be 1. K2 is load, K3 is delay. K1 and K3 have a constant of 1, while K2, K4, and K5 have a constant of 0. And MTU over here, it basically stands for maximum transmission unit, or the maximum allowable size of a packet being transmitted between two routers. So we can move on to EIGRP tuning and troubleshooting. Various techniques can be used to diagnose issues in EIGRP configuration. We mentioned hello packets a while ago, but we also have hold timers. And yes, there are also timers for descending of hello packets, and metric weights, which can be calculated with the formula that I provided a while ago. And aside from these, adjusting the timing, it's like what you do with for example, if you are working with engines, you adjust the timing belt. You can also adjust the timing for this one in order for packets to not cause a network overload. But yes, aside from that, route summarization and filtering, um, which are also core principles of the IGRP, can also be utilized through the auto summary command, a command which we will encounter later in the presentation. So a very important point, or a crucial point to remember, is key value mismatches and authentication issues may occur, even if EIGRP is a very complex but also a very refined routing system or routing protocol. We must still be aware of them, and that means that even though I did say that these are the corresponding K values provided over here, they may change depending on the situation. So be wary of any corresponding changes. But now we move on to EIGRP tuning and troubleshooting. Over here I have listed a number of commands. Well, not a number of commands, but basically various commands that are needed in order to tune and troubleshoot an EIGRP based network topology. The first one over here is debug, which is the foundation, very fundamental command in all devices in order to check if the network is actually working, or if it is working as intended. So debug eager packets. This displays real-time packet level eager communication with the following packets, such as hello, update, and query, and it is extremely useful for diagnosing formation issues between two neighbors or two different routers, update propagation problems in the network topology, and unexpected queries or replies from devices that are not supposed to really be in the um, in the network that is forged by EIGRP. Then we also have the traditional show IP route and show IP route eager protocols. This one is derived from the show IP route. This is for the router's routing table. It's gonna display it whenever you enter the command to show all known routes. And this latter one, filters to only show eager learned routes. And as you can see over here, and it will be shown later um, when I demonstrate this on in Cisco Packet Tracer, the route source code for EIGRP is D, and also to be seen in the show IP route EIGRP command is the next hop IP, or the IP of the next router, and the outgoing interface or the IP of the port where the serial cable or the CRDCE is connected, the cable that connects the router that you are operating or typing the command on with your next router of choice or the next hop IP, and also the metric and administrative distance in between these two devices. And the use case is obviously to confirm which routes are learned via EIGRP and to verify if it is the routes are installed. And we also have show IP EIGRP neighbors, which lists all EIGRP neighbor routers that have formed an adjacency and yes, have basically joined the network. So any key info about this is it shows neighbor IP addresses, uptime of the adjacency or how long they have been adjacent or connected to the network. It also uses SRTT or smooth round trip time and retransmit timeout or RTO. So basically, if a connection dies, that is what RTO is. Show IP EIGRP neighbors. Typing that command will show when a router or an end device has signed out or basically cut itself from the network, probably because the router died or lost internet connection or whatever. Yeah, that is basically what that is about. So it helps you check this command helps you check if the neighbor relationships are properly established and stable. Then we also have the show IP ERGRP topology or the show topology all links. So basically, this displays the entire EIGRP topology table since obviously it has all routes known to the route. So this only shows the feasible routes. This first the former command or show IP EIGRP topology shows only the feasible routes, while show IP EIGRP topology. All links shows all known paths, including those that aren't feasible successors, meaning those paths that have not been established or configured in order to accept EIGRP. That is shown in all links. So basically, physically linked routers which have not been properly configured yet. So over here we have successor, the best route, feasible successor, backup, report the distance, feasible distance, and yes, the use case of this command is that it helps us with understanding routing decisions, redundancy of routings, and convergence basically. Yes, without redundancy, especially since we also have there are times when routes are doubled, and we do not need that in a advanced and rather complex routing protocol. And we also have IP bandwidth percent EIGRP AS percent. This stands for like the number, the autonomous system number or the series number that that the user can enter. It could be any number as long as it is not taken by another number or another process, which is what we networkers call this one. So yes, this limits how much of an interface bandwidth EIGRP can use for routing updates. So use this command in order to set limits or to set boundaries for routing updates. So we have the sample command over here, which is IP bandwidth percent EIGRP 100 or process 100 to 50%. So basically, process 100 is only allowed to use 50% of the interface bandwidth. And the use case of such command is to prevent it from overloading slow or critical links. Or basically, this application, the application of this command is usually seen in wide area network interfaces. And then finally, we also have the IP hello interval EIGRP, or yes, the IP hello interval EIGRP series number, seconds command, and over here, hello interval is for how long the EIGRP process sends packages or packets, sorry, in order to maintain neighbor relationships, whereas hold time is for how long the router waits before declaring a neighbor down if no hello is received by the receiving router. So an example is IP hello interval EIGRP 105 or 5 seconds. For process 100, the hold time would only be 15 seconds. So tuning these values can help detect failures faster or reduce unnecessary traffic on stable links. But we're not necessarily going to use all these um, all these commands over here, but nevertheless, we will still implement them as you can see in our network topology. This is a very simple network topology over here. 3 PCs, 3 switches, 3 routers. That's it. And I also happen to have a list of commands needed for the routers, and we are going to illustrate um, how the troubleshooting and tuning process is conducted in Packet Tracer. So I'll go straight to the command line interface of this one. Okay, and we are going to program all 3 routers first. We are going to configure EIGRP in all of them in order to get the troubleshooting process started and demonstrate, of course, how EIGRP works. This is the auto summarization process that we discussed a while ago, but instead I have disabled it. No auto summary. Okay, so and as we can see over here, this is the acknowledgement of adjacency of the this router as provided by the other router. IP neighbor 10.0.0.1 is up. All right. Okay. As we can see, our third router is connected to our second router with through the use of EIGRP. Alright. Now it is time for us to implement the commands that we discussed at the end of our presentation onto our EIGRP network, as they are optimizations for performance, failover, or even traffic shaping. But I don't think we will get much traffic since obviously this is a very simple network topology. But nonetheless, let us try and encode these commands into our browser. So first, let's go to executive mode. Big T S000 and IP, the hello packet interval, we are going to set it to 10 seconds. Okay, sorry, I forgot a keyword. And usually in older packet tracer older packet tracer versions, we still have to include the hold time command. But in this newer version of packet tracer, there is no need, as the hold time the hold time feature of a router automatically adjusts to 3 times the hello interval. So if we set this one to say 5 seconds, it will automatically adjust itself to 15 seconds as it is what is programmed in Cisco Packet Tracer. But now let us repeat um, the same line of code on our other routers in order to, of course, fine tune them even more. So that now that we have fine tuned little aspects of our EIGR routing to make sure that they work, let us first troubleshoot in order to see if it actually works. So we are going to use some of the commands that we discussed earlier in the presentation, such as show IP tiger name, first command over here. And as we can see, router 1 has formed um, an adjacency with router 2, the IP address of router 2 over here. and this is for process 100, which is okay since we can see anyway. We can see that it is connected with the router 2, and it only shows direct connections. This show IP EIGRP name. Now let's see show IP EIGRP topology. Let us see what our network topology looks like. Now here we can see one successor each. One successor FD is the distance successor connected via fast Ethernet 00. So yes, that is our computer. The connection of our router to our switch, our switch to our computer. So we have checked all that. Now we can also do show out IP route EIGRP over here. So show IP route EIGRP. And as we can see, it uses the a while ago we said that the letter D is a letter or a letter that symbolizes the EIGRP connection. So 10.0.0.4 is connected via 10.0.0.2 serial 000 over here. And that means that our EIGRP is up and running. We can also use the show IP protocols command in order to see what the routing protocol settings are. And this will confirm the use of EIGRP. So D serial 000 is D, and as we can see over here, it is connected to 192.168.2.0. That means there is a route between router 1 and router 2, and also a route between router 2 and router 3. So via 10.0.02, 192.168.30 via 10.0.0.2. There we go. And we could also use the debug command was listed in Notepad over here, but it will take some time for the debug process to be finished. And sometimes in Cisco Packet Tracer, the debug process may be a little repetitive and way too hard to end on the glitches of Cisco Packet Tracer. But for now, I have some confidence in my troubleshooting of my EIGRP configuration, and thus it is time for me to test if the EIGRP has been properly configured or established in our network topology. Let me start with PC1. We are going to do the ping test in order to prove that our EIGRP works. So let us first ping router 1. It's gateway 132.168.1.1. And yes, as we can see, we already have an instant reply. And we can also do the same for the gateway of route 2.8.2.1. And we also have instant reply. We will now try the LAN or the gateway of router 3, 2.168.3.1. Instant reply as well. Now let's see if PC1 can also reach the end devices that are connected to router 2 and router 3 respectively. So 2.168.2.10. Let's see if this will work. I believe that the first packet may miss, but the next packets will connect and will be received, and there will be a reply. My prediction is correct. This worked. There's a 75% success rate. This always happens to me actually whenever I am configuring these types of protocols in Cisco Packet Tracer. The first packet misses when I am doing a ping test on one of the farther end devices, but the other three packets find their way back. So anyway, we can also do the same for PC3 2.168.3.10. I believe the first one will time out. The packet will not be received, but there will also be a reply. This is the RTO that I was talking about, request time out. But that confirms that EIGRP is working for our first PC, that our first PC can access the other two PCs. But let us also do the same test on PC2 to confirm that our EIGRP works. So ping 168.2.1. So that is the obviously the gateway um of our second router over here, or the router where our um second PC or PC2 is connected. Hold on, I forgot to put ping. There we go. We have connected ping 268.8.1. Okay. Now let us ping the devices, which I believe will also have a 75% success rate. But what matters is that it gets through the package. And wait, since we pinged a while ago, that means that the hello packet was sent, and there was a reply packet that we got immediately over here instead of a request timed out where the um the the other PC or end device did not receive a query packet. So let us do the same for IP address of PC3, or basically PC3, and we immediately got a reply packet over here. And let us do everything on PC3, everything left in my notepad to complete the ping test and also complete the troubleshooting process for our yeah, for our EIGRP. So ping 68.3.1. Let's wait for the reply packets to clear. Ping 192.168.1.1 also clear. Ping 168.2.1 clear as well. Let us see if we can reach PC1. Ping 192.68.1.10. Here we go. Ping 192.168.2.10. And there, our final four reply packets on PC3. But let us also do the ping test or troubleshooting test on our router command line interfaces just to be sure. Since obviously some people are not looked at, just the basic troubleshooting commands that I will discussed or went over in my presentation. So let us also ping 2.68.1. Success rate is 100%. 5 out of 5 packets were received, were sent, and were received. So basically went back to send. 2.ping192.8.2.1, which is the LAN of router 2, or basically the direct gateway of router 2. 192.168.3.1. Also a success. Let us do the same for router 2. 2.168.1.10. Yes, success. 2.168. Testing 2.8.3.1. Absolutely. And just to complete our troubleshooting procedure over here, 2.168.1, 2.168.2. Ping 2.168.3.10 is the IP address of our third PC. And as we can see, the troubleshooting process is complete, both with the EIGRP tuning commands that we have entered into our routers, and also the ping tests that we did along with the troubleshooting commands such as show IP route, etc., in order for us to actually confirm that that our EIGRP is up and running. And that concludes it for the discussion of dynamic routing, EIGRP, and EIGRP troubleshooting and tuning in a nutshell. So Thank you. God bless.